This next review is on probability. The first things I want to just remind you of, which we'll touch on when we go through this, but it's on your little study guide, is there a connection between mutually exclusive and independent? So if you'll recall from when we did this, when I taught you probability, we talked about a person being male and a person being pregnant. And are they mutually exclusive? Yes, these two events cannot happen together, so they are mutually exclusive. You get your Unit 5 test back and you get an A and you get a B. You can't. It's one test, you get one grade. Independence is if knowing the results of something affects something else. Knowing if something is going to happen, does it affect the results of something else? So if we know the person is male, then does that change the probability that the person is pregnant? Absolutely. If I know he's male, then I know he's not pregnant. So they are not independent of each other. Two mutually exclusive events can never be independent because if one event happens, the other event is guaranteed not to happen. And that's a great, great multiple choice question. Then you've got these. You've got to know all of these. There are a couple of these I think that are on your formula sheet, and we're going to use these as we go through this review. But there they are, and you got to know them. Okay, so I'm going to start over here. It says this topic appears in 8 to 12 out of 40 questions, so that's roughly a fourth of your multiple choice. So they love some probability and some multiple choice. In the free response, this topic occurs in 1 or 2 out of 6. So that's a sixth or a third of your free response questions. So probability is a big, big topic. I'm going to skip kind of some of this intro stuff and just get to the good stuff. I want to talk about the law of large numbers. So if you'll remember, we talked about flipping a coin, and flipping a coin, it has no memory of what it had flipped before. So if I flip it 5 times, you know, I could get all 5 heads. But the law of large numbers says as the number of times this event happens increases, the probability will even out to what it theoretically should be. It will at least get close to that. So theoretically, we should get 50% heads and 50% tails. The law of large numbers says as the number of times an event happens increases, the probability should hover close to what the theoretical probability should be. At the beginning, it can be all over the place, but it should level off. Okay. This is notice that the number of tosses increases, the percent of times that the coin lands on heads gets closer and closer to 50%. In other words, in the long run, the relative frequency of getting heads approaches 50%, which is what we expected it to be. Want to talk about sample space? A sample space is the set of all outcomes. So tossing a coin one time, I could get a heads or a tails. But tossing coin, go down here to where it says tossing a coin, tossing 2 coins, it's not just heads or tails. It's, well, I could get 2 heads, a heads and a tail and a heads, or 2 tails. So don't just think that the sample space is what each individual outcome can be. It's all the combos. Throwing a die, my sample space is 1 to 6. A tree diagram is great when you have 2 events that are happening together. Imagine an experiment in which a die and a quarter are tossed together. So this is a great tree diagram. We're going to roll the die first. So here are my 6 options. And then after I roll a 1, I'm going to flip a coin. I could get heads or tails. So the outcome here would be a 1 and then heads, or a 1 and then tails. And it just does that for each of the 6. So if I have 12 possible outcomes, then each individual outcome has a 12th probability of happening. And this is going to be your sample space. all the possible combinations. All 12 outcomes are equally likely, therefore the probability of each outcome is 1/12. It is common practice to use capital letters to indicate events. So event A, getting an even number when a die is thrown, so 2, 4, 6. Event B, getting 2 heads when coins are tossed simultaneously, a heads and a heads. But when you're finding the probability of an event, it would be the probability of A or the probability of B. It's always a capital P. This is not a p-hat or a p-bar or a p-value or a pooled p. This is just p for probability. Probability of an event is generally denoted by a capital P followed by the name of the event in parentheses. So probability of the event. And to find the probability, it's always the total number of favorable outcomes over the total number of outcomes. Applying this to the events defined earlier, A, getting an even number in a toss of a die, and B, getting 2 heads when 2 coins are tossed. So the probability of event A, which is getting an even number, so I have 3 favorable outcomes out of 6 total, so it'd be a half. So in other words, there's a 50% chance of getting an even number when a 6-sided die is thrown. Probability of getting 2 heads, well, I have 4 possible outcomes and 1 favorable outcome. So it would be a 4th. And then you've just got some basic rules and terms. You know, the probability of an event always has to be in between a 0 and a 1. It cannot ever go over 1. It cannot be negative. The sum of all the probabilities of your sample space has to be 1, has to add up to 1. The odds in favor of an event, this is something we didn't talk a lot about. The odds in favor of an event are the probability that an event occurs over the probability that the event does not occur. You can also use it with the colons. If you think about, I don't know, you may have heard like Kentucky Derby. The odds of, you know, some horse winning is like 5 to 1. So that's the probability that event A can happen and that it does not happen. So obviously that would be favored. That horse would be favored. When tossing a die, what are the odds in favor of getting the number 2? So that's the probability of getting a 2 over the probability of not getting a 2. Now, again, this is the odds in favor. So this is not the probability of it happening. The probability of it happening would be 1/6. The probability of getting a 2 is 1 over 6, and the probability of not getting a 2 is 5 over 6. And then you same change, flip that, and the 6's cancel. So the odds in favor of getting a 2 are 1 to 5. Okay, some more terms. The complement of an event is the set of all possible outcomes in a sample space that does not lead to the event. You're going to see this A prime or A C for complement. Both of those are the not of A. Disjoint or mutually exclusive events are events that have no common, no outcomes in common. In other words, they can't occur together, which we talked about. The union of events A and B, make sure you get your little symbols right. This is A and B. Union is and, intersection is or. No. No, sorry, told you wrong. Let's try that again. The union is putting them together. So at least one of the two ones. So it's the probability of A or the probability of B. At least one of the two events has to occur. So union means you put them together. Or is always a plus sign. Remember that you have to subtract out if there's overlappage. And we'll talk about some of those. Intersection is the and. And so that's the probability of A and probability of B. And that's intersection. Where do they overlap? A conditional event, this is the given. A given B is a set of outcomes for each event A that occurs if B has occurred. So that's the probability of A given that B has happened. Two events A and B are considered independent if the occurrence of one event does not depend on the occurrence of others. Just to remind you to figure out if event A and B were independent or not, you would find the probability of A given B, and then you would find the probability of A. If they were the same, then A and B are independent because B happening did not affect the probability of A. If this is, I don't know, 1/2, and so is this, well, let's say 1/4. If the probability of A given B is 1/4 and the probability of A is 1/4, then B happening had no impact on A. So A and B would be independent. But if these two numbers are not the same, then they are dependent because B affected A. And you can go the other way too. B given A, and then you would find the probability of B. And if they are the same, then they're independent. If they're different, then A happening had an effect on B happening. Some nice little Venn diagrams. You've got event A, and then its complement, the not of A. This is events A and B being disjoint or mutually exclusive. Disjoint is just another way to say that. A and B, the union of events A and B are this part in the middle. No, sorry, union is when you put the two together. Now notice that when you do this, when you do the probability of A and you add the probability of B, that this stuff in here is getting counted twice. It's getting counted for A and counted for B. And that's why you have to subtract the overlappage out. And graders are going to be really particular, especially on only on free response, about seeing those formulas. So when you're doing your homework for this stuff, I want you to really, really work on writing the formula, then plugging in your numbers. This is intersection, so this is just what do A and B have in common. Okay, independence versus dependence. Imagine that you shuffle a deck of cards and then draw a card at random. The chance of you getting an ace is the same across all suits, hearts, clubs, diamonds, and spades. In other words, the likelihood of you getting an ace does not depend on the suit of the card. So we can say that getting an ace and getting a particular suit are independent. Now consider a doctor examining patients in an emergency room. The likelihood of a patient being diagnosed for a knee injury is higher if that patient is a football player, because football players are more likely to suffer knee injuries than non-football players. Therefore, the event knee injury depends on the event football player. So they are not independent, because knowing that you're a football player ups the odds, ups the probability that you have are going to have a knee injury. Okay, so now I want you to get your notes guide out. So what we've just done is we've gone through this. Okay, so now we're going to look just at this worksheet, because I've got all the examples typed out. Here we go. The sample space for throwing a die is 1 through 6. Suppose events A, B, and C are defined as follows. A is getting an even number, B is getting at least a 5, and C is getting at most a 3. Find the probability of each of these events and its complement. Okay, now I'm going to cruise through this. This is a video, so you can pause it, you can rewind it, you can go at your own speed, but I'm going to cruise on through. Again, remember, pause it, rewind it, go at your own speed. So the probability of getting an even number, well, there are 3 even numbers out of 6. So that's 1/2. The probability of getting at least a 5, there'd be a 5 and a 6, so there are 2 of them. And the probability of getting at most a 3, that means no more than 3, that'd be a 1, a 2, and a 3. So there are 3 of them. Then the probability of a complement is just going to be 1 minus 1/2. It's just the not. So the probability of not getting at least a 5 would be 2/3. And the probability of not getting at most a 3, that means getting a 4, a 5, or a 6. So again, all of these have to add up to 1. Okay, now it says find the union and intersection and conditional probability of each pair of events. Okay, I'm going to start with a Venn diagram. I'm going to start with some sort of representation of all 3 of these events. Okay. So the probability of getting an even number, I'm going to let him be A. So an even number is going to be 2, 4, and 6. Okay, probability or event B is getting, let's do B over here, getting at least a 5, and event C is getting at most a 3. Okay, so event A is getting an even number. Okay, so that's a 2, 4, and a 6. Okay, but let's see where my overlappage is here. Event B is getting at least a 5. So 6 is a number that's at least a 5 and it's even. So he's going to go in that overlappage right there. 4 is just a plain old 4. Another number that's at least a 5 is a 5, but he's not even. So he doesn't go in the overlappage. Event C is getting at most a 3. Well, that's a 1, a 2, and a 3. Well, event A was even, so 2 is shared there, and then 1 and 3 go there. So again, it's just a visual representation of all my events, which I highly, and they highly recommend when you do a free response for probability. Okay, it says find the union, intersection, and conditional probability of each pair of events. Okay, so let's go union. And I'm just going to sort of make 3 columns, one for union, one for intersection, and one for the conditional. And I would write small. Okay, so union is my OR. So I'm going to go probability of A union B. So A means I'm even, or I'm greater than or equal to a 5. Okay, well that's, if I use my formula, that's the probability of A plus the probability of B minus the probability of A intersection B. And again, please get in the habit of writing your formulas. Okay, well the probability that I'm an A, or that I'm even, sorry, is 1/2. The probability that I'm B, and again I'm just getting these from up here, the probability of B, which is at least 5, is a 1/3. But then I got to minus something because I have some overlappage here. The number 6 is even, and it's at least 5. So he's in here twice. So I have to subtract out the overlappage. And then if I go common denominator, 5 minus 1 would be 4. So 4, 6, so 2/3. Okay. So now I'm going to find the probability of A union, or yeah, union C. And that's that I'm even and I'm at most 3. Okay, so again, let's use the formula. Probability of C minus probability of A intersection C. And again, pause it, write it out, and then hit play and check it. See if you can get this on your own. So the probability of A is that I'm even, that's a 1/2. Probability of C, that's that I'm at most a 3, that's a 1/2. And then minus the overlappage, that means that I'm even and I'm at most a 3. The only one for that will satisfy both of those is a 2. So there's 1/6. So 1/2 plus 1/2 is 1, and 1 minus 1/6 is 5/6. Okay. And then the probability that I'm B union C. So that is that I'm greater than or equal to a 5 and less than or equal to 3. So that's the probability of B plus the probability of C minus the probability of B intersection C. Okay, well, the probability that I'm a B, that I'm greater than or equal to a 5, is that B? Hold on. Yeah, greater than or equal to a 5 is 2/6, which would be 1/3. And the probability that I'm a C, that's less than or equal to 3, that's a 1/2. Minus, okay, well, what's the overlappage? Can you be greater than or equal to a 5 and also less than or equal to a 3? No, so that's a 0. Okay, so because that's a 0, what would you say about these two events? They are mutually exclusive. Their bubbles don't overlap. This is bubble B and bubble C. And you can see there's C and here's B. And they don't overlap. They don't share anything. So now I just need to go 5, 6. Okay? So those are all my unions. Okay? Now I'm going intersection. Okay, so this is and. This event has to happen and this event has to happen. So probability of A intersection B. That means I'm even and I'm greater than or equal to 5. Well, what number is even and greater than or equal to 5? That's easy. 1/6. Well, sorry, the answer is a 6. And so there's only one answer that's even and greater than or equal to a 5. Okay. Now with the probability of A intersection C. Okay, well, A is that I'm even, and C is that I'm less than or equal to 3. Well, how many numbers are even and less than or equal to 3? And the answer is 1. The only one is a 2. So there's your probability. Okay, now with the probability of B and C. That means that I'm greater than or equal to 5 and I'm less than or equal to 3. Well, that's 0. I don't have any numbers that are greater than or equal to a 5 and less than or equal to 3. That means, again, that's this piece right here. Nope, not him. This piece right here, that's a 0. That means that they are mutually exclusive, or what's the other word for that? Disjoint. Okay, so now we go conditional. Okay, so this is the given, and your given is going to change your bottom number because it's given that something has happened. What is the probability that something else is going to happen? So I want the probability of A given B. Okay, so that means that I'm even given, what was B? Greater than or equal to 5? So this is going to be, if you use your formula, which again, they're going to want to see, this is the probability of A intersection B over the probability of B. Again, it changes your bottom number. It's given that B has happened. So what is the probability of A and B? Okay, so even, given that I'm greater than or equal to 5, that's 1, because it's a 6. 6 is, so that's a 1/6 out of, okay, now what's the probability of B happening? Well, B is that I'm greater than or equal to a 5. That's 5 and 6, so that's 2/6, that's 1/3. And then if you same change flip that, you get 3/6, which is 1/2. Feel free, again, to stop, rewind, listen to it again, look at it again, look at your formula sheet, figure out which formulas are on there, look at your study guide, look at the formulas that we're using. Okay, probability of A given C. So that's that I'm even, given that I'm less than a 3. And some of you can probably just look at this and figure out what it is. That's not the point. The point is, can you show them? Can you show them that you can use these formulas? So please don't think that just because you can see it and write the answer, that's not going to get you any credit or very, very little credit on a free response question. They want to see the formulas and the numbers and where everything comes from. That's the point of the free response. Okay, so this is that I'm even. So I'm going to go probability of A and C over probability of C. Okay, so I'm even and I'm also less than or equal to a 3. Well, that would only be a 2, so that's 1/6. Over the probability C, so that's that I'm less than or equal to a 3. Well, there are 3 of those. 3 out of 6 would be 1/2. Same change, flip that. That would give you 2/6, which is 1/3. And then the probability of B given C, that means that I'm greater than or equal to a 5, given that I'm less than or equal to a 3. Okay, well, let's do the formula. So this is the probability of B and C over the probability of C. Okay, well, this is your and. So how many are this and this? And that's 0. Okay, what's the probability of C? That's this part, and that's 1/2. But obviously that's going to be a 0. But again, formula, numbers, answer. Don't just go straight to an answer. Okay. Now we're going to go to back to the notes, just for a couple more little vocab. Complement, we talked about that. Probability of A naught is 1 minus the probability of A. It's just the naught. The union, this is your addition rule. So the probability of A union B is A plus B minus A and B. That's your overlappage. If A and B are disjoint or mutually exclusive, meaning this is 0, they don't have anything in common, then you get to take him off and it's just that. Okay? So if you were going to do this on a free response, I would, and they were mutually exclusive, I would do this whole formula. And then over here, I would say equals 0 because mutually exclusive. If you know it, you need to write it. You need to show them that you know it. Don't just go straight to here because they could think, oh, you just got lucky and didn't use that extra piece of the formula. But you're not showing them that I didn't use it because I know they're mutually exclusive and I know that that part's going to be a 0. So again, you're showing them everything you know. Intersection is your multiplication rule. So the probability of A and B is the probability of A times the probability of B given A. That's if they're not independent. If they're independent, then the probability of A and B is just the probability of A times the probability of B, because they're independent. One doesn't affect the other one. Okay, then to get the probability of B given A, well, this gives it with A given B. We just did those. That's the probability of A and B over the probability of B. This guy becomes your bottom number because you are assuming that has happened already. Over here on this side, we talked about this, testing your independence. If the probability of A given B equals the plain old probability of A, or B given A equals B, then you are independent because B had no impact on A and A had no impact on B. Okay, so now we're back on your worksheet. And we got some cards. We're gonna shuffle a standard deck of 52 cards and draw a card at random. Events A, B, and C are defined as follows. A is getting an ace. There are 4 aces in the deck. D is getting a diamond. There are 13 diamonds. And C is getting a club. There are 13 clubs. So we have 52 cards. We have 4 suits. We have 13 cards in each suit. Okay, so find the probability of the following. Find the probability of A, of getting an ace. That's 4 out of 52. And you would reduce that, or not. I would say reduce it. I mean, you have a calculator. Probability of getting a diamond, that would be 13 out of 52. Probability of getting a club, 13 out of 52. Okay, now what does this mean? This is the probability of not getting an ace. Okay, well, how many aces are in the suit, are in the whole deck of cards? There are 4. Well, there are 52 cards total, which means 48 cards are not aces. The probability of not getting a diamond. Well, there are 13 diamonds in the suit. in the deck of cards. There are 52 cards in the whole deck. That leaves us with 39 cards that are not diamonds. Same thing with not being clubs. Okay, and then we've just got some nice little bitty problems, but I want you to focus on writing your formulas, not just going straight to the answer, okay? Probability of getting an ace of diamonds. Probability of getting ace, and it's a diamond. Okay, so ace and a diamond, there's only one of them. Are the events A and D disjoint or mutually exclusive? So the probability of getting an ace and the probability of getting a diamond, are they mutually exclusive? No. I can have an ace of diamonds. Stop and think what that means. Mutually exclusive means they cannot happen together. And these can. I can be an ace and a diamond at the same time. So they are not mutually exclusive. The probability of getting a club and a diamond. Okay, so you probably automatically know what the answer is, but you've got to write it out. Probability of getting a club and a diamond. And the answer is 0 because you cannot be both. Okay, and you know what question's coming. Are the events C, D and C disjoint or mutually exclusive? Yes, because they have no outcomes in common. They have no outcomes in common. That's, I can't be both. That's what makes them disjoint. The probability of getting an ace or a diamond or both. So the or is the word you want to focus on. Or is plus. Or is union. So the probability of getting an ace or a diamond. Formula, probability of getting an ace plus the probability of getting a diamond minus the overlappage. That's a D. So the probability of getting an ace, there are 4 of them. Probability of getting a diamond, there are 13 of them. Now, do I have overlappage? Do you have an ace that's a diamond? Do I have an ace and a diamond? Do I have one card that fits both? Yes, there's one of them. So I have to subtract it out. And that gives me 16 over 52. Probability of getting a diamond or a club or both. Okay, well that's the probability of getting a diamond plus the probability of getting club minus the probability of being a diamond and a club. Well, diamond, there are 13 of them. Club, there are 13 of those. And then what is this? What is the probability of being a diamond and a club? 0. And then I would make a little note. Because mutually exclusive. So then that would be 26 out of 52, which is 1/2. Probability of getting an ace given that a diamond has been drawn. Okay, so the key word here is given. So the probability of getting an ace given that a diamond has been drawn. Okay, well you can think about this. If I only have diamonds, how many aces are there? Well, there's 1. Out of, I only have diamonds. So out of 13. That's the answer. But you've got to show the formula. So for given, it's the probability of A and D over D. So what's the probability of getting an ace and a diamond? That's 1 out of 52. Whole deck. Okay, what's the probability of just getting a diamond? That's 13 out of 52. And if you same change flip that, your 52s will cancel and you'll get 1 over 13. But again, this, you will lose points. They want all of it. They want to see you use the formulas. Okay, one thing that I do want to point out, since this is our first given that we've done, the probability of A given D is 1 over 13. What's the probability of A, of just plain old A? 4 out of 52, which is 1/13. So the probability of A and the probability of A given D are both 1 out of 13. What does that mean? That means that events A and D are independent. Independent, because D happening did not affect A. A is the same by itself or with D. It didn't matter. It is the same. They are independent. But if you just read that and thought, well, surely it would matter, but if you'll actually do the probability, you'll see that it doesn't matter. Okay. 75% of people who purchase hair dryers are female. Of these female purchasers of hair dryers, 30% are over 50 years old. What's the probability that a randomly selected hair dryer purchaser is a female over 50 years old? Now, reading all of it like that, it can be very overwhelming. Just read it through once and then write down in math what they gave you in English. Okay? I'm going to let F be the event that we're female. And I'm going to let the event 50 be that we're over 50 years old. Okay? The probability that I'm a female is 75%. 75% of people who purchase hair dryers are female. So of all the people who purchase hair dryers, 75% of them are female. Then it says, of these female purchasers. Okay, now that right there, that's your given. That's your given. So the probability of something, given that I'm female, of these female purchasers, again, that changes your bottom number. 30% are over 50. So if I'm over 50, given that you already know I'm a female, 30% are purchasing these hair dryers. Or 30% of the purchasers are over 50, if I know they're already female. What is the probability that a randomly selected hair dryer purchaser is a female over 50? Okay, here's what I want. I want female and over 50. What is the probability that a randomly selected hair dryer purchaser is a female over 50 years? A female and over 50. Now, they didn't have the word and, but you've got to see it. Female and over 50. And is intersection. Okay, now think about your formula. That's the probability that I'm female times, look at your formulas, the probability that I'm 50 given I'm a female. That is straight off your formulas. Well, the probability that I'm a female is 0.75. The probability of that I'm 50 given that I'm a female is a 0.30. And then you would write a nice little sentence. There is a 0.225 probability that a randomly selected hair dryer purchaser is a female over 50 years old. You just go back and restate the question. But guys, I cannot stress enough on this probability. You have got to use your formulas. Don't go all willy-nilly crazy off on your own. Write down what they give you in math and then use your formulas for probability. Probability is probably one of the lowest scoring sections of the AP test because people abandon everything that they've learned and they just go try to wing it. So you want to get a 4 instead of a 3, this is where you can make up some ground on your probability. Okay. Company 1 has 24 total employees that are classified as associates, partners, managers, or entrepreneurs. There are 10 associates, 6 partners, 5 managers, and 3 entrepreneurs. There are 3 levels of experience within each of these classifications: entry, junior, or senior. The percentages of company 1 employees that are and an employee from company 2 needs to arrange a conference meeting with 4 employees from company 1. Okay. He gave me percentages. What I'm going to do first is I'm going to write, see all this empty space they gave us at the beginning? I'm just going to write all my probabilities. So the probability that I'm an associate, okay, well, let's look. There were 10 associates out of 24 employees. So 10 out of 24. Not even going to reduce it. The probability, I'm going to go B, that I'm a manager. Let's see, managers, there were 5 of them. So 5 out of 24. This is, I need to write manager. This is an associate. The probability that I'm a partner, let's see, there were 6 of us. 6 out of 24, partner. And the probability that I'm an entrepreneur, 3 out of 24. Okay? But then I got different levels. The probability that I'm an entry level is 50%. The probability that I'm a junior level is 0.375. And the probability that I'm a senior level is 0.125. Okay, find the probability that 2 of the people she meets with are senior managers. Okay, so guys, this is 2 events. I'm picking 2 people without replacement. So event 1 is, let's talk about the first person. Okay, ignore the fact that we're getting 2. Just find me the probability that I'm going to get a senior manager first pick. Okay, so again, I'm going to work on my formulas. Probability that I'm a senior manager. Senior and manager. Nope, that'd be B. Sorry. Did I do that right? Yeah. Senior manager. So that would be G. 0.125 and B. 5 out of 24. So 0.026. That's the probability of getting a person that is a senior and a manager. Okay. Now, the probability that I get a second one. So that's getting the first one. Okay, but I've now picked that person. So my second person has a different probability. Okay. The probability of being senior is still 0.125, but because of this. But the probability of being a manager has now changed because I already have one. So there are only 4 left, and there are only 23 people left. And that's 0.022. Okay, so I've got my first person, I've got my second person. But here's the kicker. I don't add these 2 together. I need the probability that they both happen. I need the probability that this happens and that's the key word, this happens. And for ands, what do? We multiply. So when I multiply those 2 together, always go 3 decimal places. Okay. Find the probability that 1 is a junior partner and 1 is an entry entrepreneur. There's your word. Okay? So I want the probability that I'm a junior partner. So F and C. And then I want the other one to be an entry entrepreneur. Entry and entrepreneur. Okay, so 0.375 and 6 out of 24. And that's 0.094. Let's see. Entry, 0.5. And he was entrepreneur, 3 out of 23, 0.065. So find the probability that one's a junior partner, that's that, and one's an entry entrepreneur. So for both of these two things to happen, for this to happen and this to happen, I have to multiply these two together. There you go. Find the probability that one is a senior associate and two are entry-level associates. Okay, I got 3 events going on here. Okay, find the probability that one is a senior associate. Senior and associate. And that 2 are entry-level associates. Entry-level. Is that E? And associate. Entry-level and associate. Okay, here we go. Senior associate. 0.052. There we go. Got my first one. Okay, entry level associate. Okay, now hold on. I already picked one associate out of there. So now I only have 9 out of 23 left. Make sure that makes sense. 0.196. Okay, entry level. All right, now I want another associate. Okay, well I already have gotten 2. So I'm down to 8 and I'm down to 22 people. 0.182. Multiply them all together because I need them all to happen. I need this to happen and this to happen and this to happen, so we multiply. Okay. Example 6. An insurance agent knows that 70% of her customers carry adequate collision coverage. She also knows that of those who carry adequate coverage, 5% have been involved in an accident, and of those who do not carry adequate coverage, 12% have been involved in accidents. If one of her clients is involved in an auto accident, then what's the probability that the client does not have adequate collision coverage? Okay, these are 2 events, but one's happening after the other. So I see a tree. First of all, you take all her clients, and they either have coverage, adequate coverage, or they don't. Okay, so 70% of her customers have good coverage, which means 30% do not. Okay, now she also knows that of those who carry coverage, so I'm just talking about these people, 5% have been in an accident. Which means that 95 of them have not, 95% of them have not. And of those who do not carry adequate coverage, 12% have been in an accident, which means 88% have not. If one of her clients is involved in an auto accident, then what is the probability that the client does not have adequate collision coverage? Okay, so what I'm looking for, again, I'm really working on formulas here. Okay, so here's what I want. Probability that if one of our clients is in an accident, then what is the probability the client does not have adequate coverage? So if one of our clients is in an accident, that's my given. So given I know I've been in an accident, what's the probability that we don't have good coverage? So that's what I'm looking for. No coverage given I was in an accident. If one of our clients is involved in an accident, so that event has happened, that is your given. Of these, I want to know who does not have good coverage. Okay, and again, I'm working on my formulas. Okay, so given, look at your formula sheet, look at your givens. That's going to be the probability of no coverage and in an accident over the probability that I've been in an accident. Okay, well, the probability that I have no coverage and I was in an accident. Okay, let's look at my tree. No coverage and in an accident. So that's 0.3 times 0.12. Okay, that's the top. Now, the probability that I was in an accident. Now, that can happen a couple different ways. I can be in an accident this way, or I can be in an accident this way. And I have to cover all of it. This just says that given that I've been in an accident. So I could be 0.7 times 0.05, or, that's your plus, 0.3 times 0.12. Okay, so make sure you're good with the formulas. Then we get to here. I remember when we went over this, some of you had a little difficulty typing this in. So hit pause, type this in very carefully, making sure everything goes on the bottom that's supposed to go on the bottom. The answer is 0.507, but hit pause, take your time, plug it in. The last thing you want to do is have the perfect setup, but miss it because you can't type it in right. Okay, last one. Hang in there. Last one. The local Chamber of Commerce conducted a survey of 1,000 randomly selected shoppers at the mall. For all shoppers, gender of the shopper and item shopping for was recorded. The data is collected was summarized in the following table. So we got males and females, and they were going clothes, shoes, or other. And we got 1,000 people. Okay, so here we go. Now using a table, nice and easy. Nice and easy. Okay. What's the probability that the shopper is a female? So I want the probability that I'm female. So how many females do we have? 750 out of 1,000, which is 0.75. What's the probability that the shopper is shopping for shoes? So I just want the probability that I'm shopping for shoes. Okay, give me total shoes out of total shoppers. Easy. Cruising through this. Okay, what is the probability that the shopper is a female shopping for shoes? Okay, think about what that would look like. Probability that we're female and shopping for shoes. Okay, now look at your table. You can really use a table here. Female and shoes. Find me females that were shopping for shoes. That's 230 out of 1,000 people. What is the probability that the shopper is shopping for shoes given that the shopper is a female? Okay, let's write it out. Probability, shoes, given, female. Okay, now use your formula. That's shoes and female given female. Okay, shoes and female, that comes from the problem right above it. And the free response questions on the AP test will do this. They'll build. So you don't have to go find that again. It's right here. And then the probability that I'm female, well, that's from part A. There you go. Are the events female and shopping for shoes disjoint? Okay, female and shoes mutually exclusive. Do they overlap? Well, yes, I have females that shopped for shoes. I had 230 of them. So they are not disjoint. They are not mutually exclusive. If they were, there would be a big old 0 right there. So no, because 230 shoppers were female and shopping for shoes. Are the events female and shopping for shoes independent? This is not something you can just look at. You need to mathematically prove it. Okay, well, I can try female and shopping for shoes. Now, we've had a lot of females and shoes in this problem. So here we go. Check this one out. I got shoes given female. So I'm going to use that one. So shoes given female. And that was 0.3067. Now, what do I need to find to prove my point or to answer the question? I need to find the probability that we're just shopping for shoes. Because I need to see if being female affects the fact that I'm shopping for, or affects the probability that I'm shopping for shoes. So for shoes, we found that in part B. That was 0.255. Well, because these are not the same, then being female affects the odds that I'm shopping for shoes. So no, they are not independent. Okay, I know that was a lot. And the nice thing about having this on a video is that you can go back and you can rewatch it. And guys, I'm not kidding. Probability is going to be some of your downfalls on this AP test. This is something that you don't have to like, but you have to know these formulas and you have to know how to use them. Okay? Multiple choice questions can be crazy tricky. I mean, this one down here, I mean, when you read that, it sounds like a tongue twister. It sounds like a Dr. Seuss book. But if you'll take it and break it down into a tree diagram, it's super straightforward. This one with the hair dryers, I mean, that sounded like mumbo jumbo. But if you'll take this, what's written in green, and just take your time and write out what you're given, and then write out what you're trying to find and use your formulas. Don't go rogue. Don't go off on your own. Use those formulas.